Okay, then which is going to be our final technical lecture of the semester. I'm going to develop a very simple ray tracer showing you how, at least in pseudocode, it's very, very easy to design it, or at least start with it as a very straightforward recursive format, and then we'll look at a little of of how you implement the various functions that are inside of that recursion. The two things I'm going to look at is really just the simple shapes that we work with, in particular quadrics and flat polygons. And there, if you're going to start building a simple ray tracer, this is something that every one of you should be able to do fairly easily. If you take, I forget the number, there's 412 and 413. One of them is based on ray tracing, and one of them is based on the pipeline architecture. So going back to the beginning, and we've seen this picture a number of times, is that the basic idea of a ray tracer if you collect the light that comes off of a light source that goes through the center of projection in the lens of the camera or into your eye, that would account for that would really describe what you see. The difficulty if you take this approach is what do you have to do? Well, you have too many rays to consider here. That's why we're going to switch to ray casting and only look at ones that, if we reverse the arrows, we know are going to matter. But the other part of this is that we have to compute what happens every time a ray of light hits an object. We have to, one, compute that intersection, then look at what happens, how much light is absorbed, how much light is scattered, and for the scattered light, how is it scattered? Is it a perfectly diffuse surface? Is it a highly specular surface, or somewhere in the middle? And then if there's a transmission, like what we see over here with this sphere, then each ray can generate more than one ray. If it's a surface that doesn't allow any transmission, then each ray bounces off, and if it's an ideal reflector, generates exactly one ray. Here, if you have a glass ball, so we don't have to worry about diffusion, we generate two rays, and as we'll see, we'll get something called a ray tree out of this as we start following all the rays. So in principle, you should be able to handle all possible physical interactions with this model. It's pretty general at the level we described on the previous slide. The problem is that's not a very good computational model. First, because if we follow, as we said, if we follow all rays, we only see very few of those, a tiny fraction of this infinite rays that are going out. So the first alternative we're going to make is as we've seen before, we're just going to ray cast, and then we say, well, if you start with the fact that only rays that enter the camera and only rays that enter the eye really matter, then what we can do is just reverse the direction, start at the camera, and start casting rays out. Most people, at least in this country, still call that a ray tracer, something that does that. In other countries, they tend to call that a ray caster, because that's really what you're doing. But it's the same thing. So how many rays do you need? Well, the minimum is one ray per pixel, because if you go back to when we first discussed rendering, and we said, well, you have to loop over all objects, and you have to loop over all pixels, you have to have then one ray for every pixel. It also says if you're looping over every object, and here's where the real computational difference comes in, because in some ways this looks like what a pipeline architecture has to do. It has to color every pixel, it has to deal with every object, and if you think of this on a pixel by pixel basis, well, is that getting close? Well, not exactly, because if you really want to take care of all the interactions, then you need to have all the objects and all the light sources available all the time, because when I cast a ray through this pixel, how do I find out which objects it's going to interact with if I don't do an intersection between, for every ray, compute the intersection with every object, and then if all the objects are opaque, then I just keep the closest intersection and then move on from there. So for a long time, the big problem with ray tracers and implementing them has been that you need to have all of the geometry around all of the time, and that could be a memory issue in addition to the problem of once you start talking about more complex objects, then the calculation of the intersections can be problematic. But one thing I should mention, lest I forget later, is that there's a lot of interest in how one can use a GPU to do a lot of this, because if you look at this picture, there's a lot of this in common with what we do with the pipeline, that we look at intersections with pixels, and we know how to do some of these computations. So a lot of people have looked at trying to do at least part of the ray tracing operation with the pipeline because of the speed of the GPU. And I suspect with technologies and software like OpenCL, which is coming, just announced is available for the web as WebCL, the ability to do parallel computations in the GPU independent of the graphics may mean that this kind of ray tracing will be done much more in real time within a GPU. So I keep track of what's going on in the literature. It's certainly been of interest for quite a while. But let's now just turn to what happens when we deal with quadrics. One way that's important with quadrics, and we haven't really studied this, is we've mostly dealt with objects that we say they're surfaces. They're defined by their surfaces. And there's a real limitation to that. There's a short section in the book about constructive solid geometry. In constructive solid geometry, your primitives are solids, not surfaces. So if you think of a cube as being made up of 6 little facets, that would be the kind of view we would have with pipeline architecture, and then we get a cube by knowing how to render all of these little facets. In constructive solid geometry, the cube is a primitive. A sphere would be a primitive. And one of the nice things about that is you get to use the solid properties of objects. I mean, if you're doing some sort of CAD modeling and you're working with real materials, they're not surfaces. They're materials that have properties like what kind of metal you're working with. It has a density, it has a weight, it has a cost, and you can't really do that very well if you're working only with surfaces. So there's a lot of advantages to working with solids. If you start working with how you build objects from these solids, it turns out the natural tool is set algebra. If you think of there being a set that describes the object, so you have a cube and you say, well, all points that are members of that cube are the ones that are inside of that cube, defined by, say, if it's a cube centered at the origin by x less than 1 and bigger than -1, and y the same and z the same, then you could talk about the set of points that are inside of that cube. Likewise for a sphere. And then the natural way to start building up objects is to use set operations like unions and intersections and differences. So for example, if you wanted to take a cylindrical hole out of the middle of a cube, that would be the set difference between a cube object and a cylinder object. And because they had solidity and parameters that were associated with being a solid, you could then do things like figure out the weight of the new object, the center of mass, and other kinds of properties that you might want to have in a CAD system. So this is an alternate to the kinds of things that we've been doing. But let's go back to dealing with surfaces for our simple ray tracer. So the simplest way to do that is to look at it as follows. The sphere is a quadric. So if you say what's a sphere around the origin, x squared plus y squared plus z squared equals r squared, and the ray is a parametric form, then I can write the ray. Let's suppose this is the initial point p0 and it goes in a direction d. D is just let's stick to 3 dimensions. D is just some dx, dy, dz that determine the direction. P0 is just at x0, y0, z0. So this line or the ray going out infinitely potentially from this initial point is just of the form that we've seen. It's P0 plus some alpha times d. Well, you only have one parameter. If I stick that equation into the equation for the quadric, x squared plus y squared plus z squared, you wind up with an equation with all constants except it has up to quadratic terms in alpha, and that if that's quadratic, then we solve for it. And as I think we've said this, talked about this a little before, you get the quadric has potentially 0, 1, or 2 solutions. If there are no solutions, that means that this ray misses the sphere. If there's one solution, the ray is tangent to the sphere. If there are two solutions, one is the point where it enters the sphere, and the second corresponds to the point where it leaves the sphere. So you can always find the first intersection. And that's certainly true of any quadric, and that's what makes, as we've said before, that it makes doing ray tracing with quadrics very, very easy to do. Now, the next step is once you've found the closest intersection, we could think of a scene with a bunch of quadrics now. We'll add polygonal objects a little bit later. Now what I have to do is find out, once I've found the closest intersection along the ray, I have to figure out if that point is lit or not. So now I cast rays again, and what I do is I can, from this point of intersection, I can now, essentially I'm doing some sort of a hidden surface removal here, very similar to what we did when we talked about methods for dealing with shadows. I do a calculation to each of the light sources, but I need to know about all the other objects for that calculation in order to see if any of them are blocking me from seeing, from light reaching that point on the surface, including the back surface of the object itself. If this is really behind here, the back surface of the sphere is going to prevent any light from this source from hitting the front of the sphere. So those are called shadow rays or feeler rays. They're feeling the environment to see if they can find any light sources, or equivalently, they're determining if that point is in shadow. Okay. Now reflection says, well, you've got to just keep following more rays, and here's where we start getting into the complexity. Certainly what I can do is follow this ray, and then again I have to do this calculation with all the objects to see if this reflected ray hits any of the objects in the scene, then cast feeler rays from that point to see what happens. And you can see what happens now if rays bounce and they hit this object and they hit another object and they hit another object, and maybe eventually they're going to hit a light source. Generally what you do is you realize that every time you hit a surface, some of that light is being absorbed. If you go backwards now from the light source, some of the light is being absorbed here. So not all of it is going to reach this sphere for a real surface, and if there's too many bounces, you eventually wind up stopping it and saying, look, there's just not enough energy left here to be visible in the scene. Of course, if we have reflection, then we have transmission, so you can now also follow the transmitted ray. And this is what's going to make everything recursive, is that what I do for the reflected ray is exactly what I do for the transmitted ray. And in fact, what I do for the first ray that I cast is the same as what I do for each of these rays. Namely, I go out and see if they hit any objects or they hit a light source. So I should be able to write that down very, very simply and elegantly. Now, one way to look at that is a ray tree. If I look at the ray going out from the eye that hits this surface, then, well, let's do it this way. If I were to do it from the light source, this is maybe a better way to look at it. If I reverse the arrows and look at this ray coming from the light source, it hits here and it transmits and it reflects back to the eye. So it generates a transmitted ray and a reflected ray. The transmitted ray, likewise, can hit a surface. It can generate a transmitted ray and a reflected ray. The reflected ray from the second surface can hit another surface to generate another transmitted ray and a reflected ray, which in this case goes back to the viewer. So that determines what we call a ray tree that might look something like this. That the transmitted ray generated 2 more rays. The reflected ray off of that point generated 2 more rays. Now that looks good, and this is, in fact, if everything was highly reflective and we said it was a whole bunch of mirrors, this would actually work just fine. The problem is what happens if where you do the intersection scatters the light. And at this point, we could really be in trouble, because if we use our model, and there's no reason we shouldn't use our model of diffusion or modified Phong model or anyone else that you prefer, then we have a problem, because what we should be doing now is when light hits this surface over here, just to get started, light can goes equally in all directions if this is an ideal diffuser. Well, I can't trace all those rays. And this is why, if you go back to the previous lecture, I talked a little bit about path tracing, because you could say, well, why don't we randomly trace as many of those as we can? But in a classic ray tracer, you just say, I can't do this. Well, what we do to sort of minimize the error, because it's definitely going to be an error when we don't trace all those rays, is I compute a local color at this point. So if I'm looking at this point, and this point I can see the cast ray sees the light source, I could apply the modified Phong model here, get a color, a local color, and then I could follow the reflected and transmitted rays. So likewise, when you get to this point, you're going to do sort of three things. You're going to go and follow the transmitted ray, you're going to follow the reflected ray, and you're also going to get a color component over here, which is based on whatever model you're using for the surface computed at that point without tracing extra rays. So that sort of gives you reasonable looking things, but not necessarily physically correct things. And if you really had diffuse surfaces, that's where a radiosity renderer, like we talked about in the last lecture, would work better for that case. But we're saying we're talking about ray tracing here, so let's now actually talk about some pseudocode for the ray tracer. So as we said, we can express it very simply, recursively, and then later take the recursion out and replace it by some looping or an iterative replacement of the recursion in our pseudocode. And the fundamental operation we're always going to have to do is, for each ray we trace, we're going to have to find the closest surface it hits. So I'm going to have to intersect that ray with every object in our database, unless we try and do some heuristics on that, which people do a lot of, and then compute the lighting at the surface. That's what we just said. We'll apply the modified Phong model there. And then we'll do the same thing with the reflected and the transmitted rays, taking into account that a lot of the energy might have been absorbed at that point. So when we do the reflected and the transmitted rays, they're less energetic than the first ray. Okay. When do we stop? Well, we stop if we're keeping track of how much light is absorbed. We can just say, well, there's no energy left, stop doing it. We can also do a finite number of steps and just say, well, look, after 5 bounces or 6 bounces or how many you're willing to do, there's just not enough light being contributed to continue any further. Just do a fixed number of steps. The third way that's very nice is, and this again gets us to some of the ideas that are in path tracing, is put a big sphere around your problem and say, look, all the objects are in there, so any ray and then treat that sphere as another object. And then anytime a ray hits that sphere, you say, oh, well, that ray's going off to infinity because there's no other objects out there for it to intersect. So that's another way of sort of making the recursion eventually stop. So here's the pseudocode for the recursion. Just say, okay, I'm going to trace a ray that starts with some sort of a point object. It goes off in a direction D, and I'm going to keep track of how many steps I've done. This is a little more C++ or C, a little pseudocode for that. And then the color that I'm going to output of this is eventually going to consist of 3 parts. A local part that I compute at the point of intersection, and whatever comes back from the reflected ray and from the transmitted ray. So the recursion kind of looks like this. You're going to have to keep track of normals for doing the lighting calculation at a given point. Q is going to be the point of intersection. So if the steps are greater and I just started this thing, then I return the background color. I'd say this is essentially saying when you're outside of that sphere, you're going to have some background colors, so the blue for the sky or black or something. But the heart of it is here. Compute the intersection with the closest object. If it's a light source, then you're going to this intersect means intersect with all of the objects and the light sources and return back the closest point. if that, and it's going to tell me if that's a light source or if it's an object. If it's a light source, then I just return the color of the and intensity of the light source. If it doesn't intersect anything, meaning it hits the sphere, then I'm going to just say the color is the background color and return. And otherwise, I have a point of intersection. I can compute the normal there. I can compute, once I have the normal at that point, and I have the direction of the ray that I cast, then I could use that normal to now compute reflection at the reflected vector at that point, what direction it's going in, and the direction of the transmitted vector at that point. I compute the local color given the Phong model or any other one I'm using, and now I just call myself. I call myself and I increment the step count. So I go off in the from that point, I go off in the reflected direction. From that point, I go off in the transmitted direction, increase that, and I return at the end the sum of the local color I computed with the Phong model plus the color that's returned from the reflected ray and the transmitted ray. So the pseudocode is incredibly simple. What was that, about 10 lines of code or something? And that's right. And you can now take that apart and do it. Now, where's the hard part? The hard part is hidden back up in here. This is really the work. Computing the color at a given point, well, we know how to do that, and we can do that in shaders. That's no problem. This is the big deal here. This is how do you compute the intersection with the closest object, and that, as we've tried to point out, depends very much on what kind of objects you have. And so the ones of interest to us are in particular quadrics. You can, as we'll see in the next slide, you can get equations for any implicitly defined parametric object. The problem is that you get a very high order polynomial. It just explodes on you. It goes up, kind of exponentially as you have the order of the implicit surface goes up. So it turns out to not be very practical, but people sometimes approximate that. Planes and polyhedra are of interest, and parametric surfaces, same problem. There's a method for converting a parametric surface to an implicit surface, but the problem is that increases the order of the polynomials you're dealing with even more, so it's probably not practical. These are the three that we really care about. But the general form looks like this, as we've said this, that the ray has a single parameter in it. Here I'm calling it t, the ray from p0 in the direction t. I stick that into the equation for an implicit surface. So this is just some arbitrary function of x, y, and z. Once I put in p of t, it becomes a scalar function in t, but generally highly nonlinear, and so in general I can't solve it other than by numerical methods, and even that makes it impractical for doing for every pixel. But for a quadric, then we said that we've done this when we talked about curves and surfaces. Every quadric can be written in this form, where A is a symmetric matrix. I stick this in. Now I get, as we've said, a quadratic equation, and I can solve that. Here's sort of the example for a sphere. A sphere can be centered at the origin or centered at a point C. PC looks like this. I stick in P0 plus TD, and out comes this, you can see, P0 is just 3 constants, D is 3 constants. So everything in here, I've collected the terms. This is the quadratic equation you get in T, and we could solve that for the entry and exit points, assuming the ray goes through there. Now, what do you do with planes? Let me finish up with that and polygons. Well, a plane is pretty simple. You can do the same thing. You could say, here's the general equation for a plane in terms of a normal, and C is essentially how close that plane comes to passing through the origin. Obviously, if C is 0, this plane goes through the origin. If C is positive, it's on one side of the origin, and if C is negative, it's on the other. But any plane can be written this way. If I stick in the equation of a ray, then I get a linear equation. I solve it for t, and this is what I get. It's a little more difficult if you say, well, what about a polygon? Well, if you say a polyhedra is made up of polygons, it's a little more difficult because I can intersect with each plane that it goes that ray goes through for and do some sort of testing for that point. But I need to know if that point that I computed on the plane is actually in the polygon in that plane. And there's some tests. I have one of those tests that's in the book, and it's based on this idea that if a ray enters a convex object, it can only enter once and leave once. And you can argue based on the surfaces or the lines that in a two-dimensional case, this work. Essentially what happens is if you work with a three-dimensional polyhedra, it enters one face and it leaves another face, and there's some very neat methods for finding that out. If you're talking about a polygon, a flat polygon that's convex, a line passes through it, enters it once, and leaves once, and you could argue in terms of the equations that form the sides of that line, and that's really easy to do. It's kind of a cute algorithm. But I'm going to stop here because once we get past this point, dealing with ray tracers gets much more complex, and you have to deal with issues like how do you get rid of the aliasing in it, because one ray per pixel is really minimal. How do you deal with energy? And then you get into methods like path tracing and that, and I'll leave that for another course.